All right, so there's a lot of tedium in this calculation, but it's just a matter of, taking a deep breath, not getting overwhelmed, being organized and neat as you write. Surprisingly important, when you're doing a tedious calculation, is spread things out, space things well, make sure you can read your own handwriting. I've broken that rule more than once. So anyway, let's dive in. Okay, so here's what we're going to be doing is computing the divergence. And I'm just going to do part 2 here. And so this is the vector field of which we're taking the divergence. Now notice, side note, we're exempting the origin, because if you plug in x equals 0, nothing's defined, right? It's 0 over 0 for all the whole thing crashes and burns. Okay. Alrighty, so here it is. Let's notice some patterns real quick, by the way. The first component, P, looks a lot like the second component, Q. It's just that the numerator is different, right? And then likewise the third component, R. So once you've computed that term, oh, and by the way, even better coincidence, we're taking a partial with respect to x, and that numerator is x, and then over for the next one, it's a partial with respect to y, and the numerator is y, and there really is kind of an analogy there. So once we've done one of these terms, the others are kind of pretty similar. Okay. Okay. So now, procrastinated as much as I can rationalize. So negative x divided by, and I have x squared plus y squared plus z squared to the 3 halves. Okay. Yeah, oh, thank you. Yeah, that's very convenient. Okay, so p is negative x over x squared plus y squared plus z squared to the 3 halves. Okay, so let's compute the partial of p with respect to x. That's that first term in the divergence formula. Alright, so we need to remember the quotient rule. Remember the quotient rule? Okay, I'm going to confess, I always get confused as to where the minus sign is. And I think I remember that it goes like this. Tell me if I get this wrong. So I start off by taking the derivative of the numerator and then times the denominator, and then minus the numerator times the derivative of the denominator, and then we divide by the denominator squared. Now, conveniently, well, yeah, let me not give anything away. Okay, so there's that, right? Okay. Yeah.
Do we? Oh, okay. Sorry, you haven't written it out yet.
Yeah. Oh, yeah. I've got a bunch of. I'm taking this one little step at a time. By the way, it's another little bit of advice I'd give when you're doing a tedious calculation. Don't try to do too much all at once, right? Because it saves a lot of ink, pixels, but it does cost you in terms of confusion. So, yeah. Okay. So, all right. So now let's follow the instructions that we've just written down here, and so I get negative 1 times, and then I have x squared plus y squared plus z squared to the 3 halves. Now I have a minus and a minus, so I'm going to just rewrite that as a plus. X times, now I've got to take a derivative. I've got to take a derivative of that thing. Okay, now the derivative of that thing, 3 halves, x squared plus y squared plus z squared to the 1 half, times now the derivative of the inside, the chain rule, which is 2x. That's my numerator, and it's divided by the usual denominator. Okay, let's take a pause on that. Is everybody happy with Cool? Okay. All right. Okay. Okay. So let's rewrite this a little bit. There is a common factor in the numerator. Actually, there's a common denominator as well. So I'm going to take away. There's a one of these square root of that thing. So this thing that I have circled here. That's a common factor. So let me pull that out of all the terms, and so that gives me negative x squared plus y squared plus z squared. Okay, now let's be careful here. Plus, oh, hey, cool, good news. That cancels that. Yeah, and I've already canceled that. And all I have left is 3x squared. Okay, that's nice. Let's see now. Let's not forget we canceled a common factor of that thing to the 1/2, and so all that remains down here is 5/2. Everybody good so far? Yeah. Okay. Okay. All right, so we're 1/3 of the way through this calculation now. Okay, but it's actually much better than that. So keep in mind this was the partial of p with respect to x. Now, I'm going to say, no surprise, the partial of q with respect to y is very, very similar process. And I'm just going to write down what the answer is. Totally by analogy what we already have. It is minus x squared plus y squared plus z squared plus 3y squared over this same denominator. And then the partial of r with respect to z. Pattern, again, same deal. Z squared. Okay, and so we're asking then what happens when we add these three things up. And the good news is that, let's count, they all have the same denominator, right? Let's count x squareds. They all cancel. That's kind of cool, right? Okay, now let's count y squareds. They all cancel. And then let's count z squareds. Those all cancel. Everything cancels, and the answer is 0, which is awesome. All of this adds up to 0. Well, not that bad. So I lied a little bit when I said we were only a third of the way done. We were like almost done. We just, Now you should, on the homework, you got to actually write out, these calculations. But the point is, it's just a matter of taking a deep breath and doing it and noticing the exact same patterns and same argument. Everybody happy?
Yeah.
Okay.